I was here about 5 years ago, and I'll talk about some work which was done with my all too short postdoc with Danny, but it's been great working with Danny on discrete state spaces, and that's work that I first talked about a bit in IPAM last time, and I'll talk about some more. And then talk about some work trying to generalize this to more general state spaces, which I've been doing over the last few months, last year or so. So I've tried to have an exhaustive list of people who were involved in producing images over the following slides. I now realize there is a name missing, but I cite him later on anyway. So definitely there's lots of work done with Cosme Maranika's group in CA-Saclay, and some of the work which, in fact, now I won't talk about so much because this is nice pure mem stuff that Petter really talked about, and this is following from collaborations with James. Petter couldn't be here because of visa issues, but it's quite a cunning plan he has, because now he gets both James and I promoting his work, so it actually works out quite well. And then some stuff I'll talk briefly about work done with David Wales and his group in Cambridge as well. So don't really need to convince the audience here. Well, maybe I need to convince some of the audience, but when we can get down to the atomic scale, we can really have this time and space resolution that you can't get with any other methods. I'm not going to do the BMW to Schrodinger type plots, but I think we kind of get that sort of context. But because of this resolution, this is nice because we hear all this detail, but then we actually try to reach to the scales, time and length scales of experiments or other applications or other higher scale models. We really have to try to coarse grain. So we have to try and distill some of this atomistic data in space or time and try to produce models at higher length scales and higher time scales, longer time scales. And typically, Danny talked about this nicely in the last workshop, but when we can, with a lot of these empirical potentials, as they're short-range force fields, as we've seen, we can parallelize quite easily in space. In a sense, I can go to larger systems with a larger machine, but it's quite hard. It's very hard to go in time. So you can think about this with, I don't know, if you're trying to cook, if I have one chicken and I have one oven, I can cook my chicken. If I have 10 chickens and 10 ovens, they cook in the same time, but I can't multiply the temperature by 10 and cook my chicken in 10th of the time. It doesn't scale that way. But so we can go, space is quite easy with enough resources, but time can be much harder. So typically when we're building, when we are coarse-graining models, we rely on some measure of human expertise, typically to qualify the uncertainty in our model. So we have some application domain we know about, some regime we know about, and we can then use our domain expertise to assess whether we trust that model for its application, which is great. And it's often the best thing we can do. But if you think about training somebody, it takes a long time. And also, if you want to try to work at scale, where I have to do many decisions multiple times a second, humans aren't the best option for this. So ideally, we want to try and develop some sort of autonomous measures of uncertainty that we can apply to every second or 10 times a second, which we will frequently get to if we're applying things on 100,000 cores or this exascale type scale. So we want to have some qualification or quantification of uncertainty on the future behavior of simulations. Is quite hard to define, but typically because we're going to be using models at larger length scales and larger time scales, we actually need to have some form of uncertainty prediction on this. So I'll talk about two parts. So part one was we really work with Danny, where when we are thermally activated, we can actually make this uncertainty quantification quite well defined, and we can actually use it to manage, effectively achieve this type of idea where we use UQ to manage resources at scale. And then I'll talk about slightly more general work where we can make some progress for quite a large class of systems if we go to a discrete continuous state space using ideas from these machine learning potentials. So first part, I guess many people know this from atomistic simulation. In general, if we're doing some atomistic simulation with an interatomic potential, and I won't really talk about uncertainty or any properties of the interatomic potential at all in this talk, we have some potential energy function. It takes the positions and it gives me an energy. And this is when I have lots of atoms, this is a function in very high dimension. And it has many minima and many saddle points. And all the minima are these stable configurations. And so we can think about building what's called an energy landscape of these. So we have our minima, local minima of the system. And they typically are connected by mixed mode saddle points between. And we can visualize this high dimensional system through a tree graph or a connectivity graph where each vertical line is a state and the joining points of the branches give us an idea of the height of the saddle points. So there'll be a few larger graphs in the slides that follow. And what we often find is that these energy barriers, the distance between the minima and the saddle point is much larger than the thermal energy. And in that regime, transitions are rare. By rare, I mean because we have to resolve thermal vibrations, we have to have a femtosecond type time step to MD. And for very reasonable values, half an electron volt, 300 Kelvin, we can look at about 1 trillion MD steps to see a transition. So this is bad from a sense of computational aspect. From a theoretical aspect, it's actually quite nice, because what we know in this regime is that we have this nice separation of timescales. So we have what we call a spectral gap. So the phonons, or the thermal vibrations, decorrelate on a timescale far faster than the timescale for any structural changes. So we have this nice, from a theoretical analysis of the dynamics, we have this nice property that we have this. This is effectively a sort of Markovian type system. So this was really formalized by Danny, Claude Lebris, Tony Leliev, and Mitch Luskin, in a really nice paper from 2012, which I didn't give the journal for here, but it's Monte Carlo methods and applications. And so this is a way of saying that if I treat my potential well, which one of these minima, as a Fokker-Planck equation with absorbing boundary conditions, I can show that on a time scale, when I have this property, when I have a deep well, I have this spectral gap, and on a very short time scale, the decay of probability out of my basin follows this simple exponential distribution. And this is effectively the underlying law of Kinetic Monte Carlo and all these Monte Carlo models. So when I do that, I can look at transitions, I can use my rate theories, and I can start to build up a network of states. And I can use my rate theory with this well-defined time-independent rate constant. And this works because I have a time-independent rate constant for the exit from my basin on a time scale longer than the picoseconds required for phonon decorrelation. So the real takeaway here is that when we have this thing that is hard computationally to generate transitions, the theoretical characterization of those transitions can be quite simple. So we have this nice Poisson-type probability. The probability of being in some state after a time t for a given value of my total escape rate is just this nice exponential decay. This is really nice. But unfortunately, there's many systems where we don't really have this nice separation of timescales. So you can think about some dislocation networks or even just big nanoparticles where there's always something happening. The timescale for glide or other processes is on competing with phonons, with diffusion, and all sorts of things. And we often, especially when we start applying, this is a uniaxial tension, so you really see lots of stuff happening. There's all of this, it's a big mess. So here we can start to make some progress if we think about ensembles of systems, which I'll get to in the second part. So that's the two parts. We'll talk about one bit where we have this nice spectral gap, but we're thermally activated, and one bit when we don't. So this formal connection was really put in a really rigorous setting by that paper I mentioned earlier, but the general idea has been around for many years, and Kinetic Monte Carlo models is really a workhorse of material simulation. And there's many ways of trying to explore this landscape and building up a network of states. And many of the people who've pioneered this are in the room. So there's methods based on curvature, so from Norman Mousseau and Laurent Belland, and Graham Henkelman looked at different methods based on curvature. There's the methods that we'll really use here, so from the Los Alamos, so from Danny and Perez and Art Vota. So heating up, just to make things happen quicker because it's hotter, and parallelizing, which again, I'm trying to sort of, have some form of compression on the slides, but this spectral gap and this Markovian property really allows us to generate many samples in parallel because we have this memory-free property. So this is really the foundation behind parallel replica dynamics and more generally the path-splice idea of Danny, which is what we build on really. So we can heat things up and we can duplicate. We can also try to change the potential energy surface itself, which I won't really talk about, and we can also start to sort of speculate long moves in the energy landscape. That's what David really does, which again I won't really talk about here. Though we did do some work trying to do some UQ on this speculative stuff as well. So as I said before, we want to try to really put some UQ on this process, and then maybe we can use that to help us try to build these type of models on a big computer. So this is the idea that if we have here, if I've done some work and I've found some states, and now I found all the black lines, and imagine, I had some omnipotent being that could tell me all the possible states in the system would be the gray lines. My yellow dot is my model trajectory, and at short times it follows everything's all right. But if I run for long enough, I'm going to have the perfect model would leave the state space of states that I found. This is a sort of Rumsfeldian process, right? So here this is now a new state. So I can always write down for any given state in my system, the total escape rate from some state is the sum of all the exits, which I can partition into the exits that I've seen and postulate some rate for the exits that I haven't seen. So this is in principle exact. I mean, if I knew these unknown rates exactly, then in a distributional sense, the dynamics on my system would be exact. So we can, and again, we can represent all of these rates to unknown rates, just to a single absorbing state that represents all of our ignorance about the system. So everything we don't know is just characterized by a transition to this unknown state. And these sort of ideas have been around for quite a while. And what we really did with Danny was try to look about how we can try to estimate these rates in using the fact that we know that our escape rates follow this Poisson type behavior. So we actually put all this into a code that we call Timbre. So this is sort of we're in this, because of the program, we can scale, we can get to big systems. And I'm going to try and quickly go through all the different things that we do here. So effectively, just to give a sort of the setting, we're effectively running high temperature MD with many, many copies of high temperature MD. And when we're running on, say, 100,000 state cores, there's 100,000 different MD jobs, and we have to work out what states do we give to which workers to actually generate data. So in practice, what we do is that, say for one single state, I take 4 copies of it, I thermalize it, and I start running. We do how we do the temperature acceleration, all the other things I'm not really going to go into, but we have some way of optimizing the best temperature to run at based on the past sampling data as well. And then after some time, and these are all done just allocated randomly, and I randomly start connecting. They're completely uncorrelated events, but as long as the order which I receive has no correlation with the order that I send them out, then at some point, one of these guys might make a transition. So I can then collate all of these times and say that my first passage for this particular transition was, for example, 4 blocks of this time. Then I can work out a rate for this process, and then I can, at some later time or some other time in the simulation, I put myself back in this state. I do, say, 3 copies, and I run. I see nothing. So now I've got about 7 blocks of waiting time and a first passage time for this transition of 4 blocks. And so I can continue this process, and after some computational time, I've accumulated a catalog for every single state of set of rates, connecting states, the first passage time for those transitions, and the total amount of time I've spent in each state. So that gives me all the green. That gives me enough for this. So how can I use that to try to estimate these unknown rates? So what we're really using here is that we can use this nice Poisson probability property of our dynamics, which is we only really have in this rare event regime. So if I I know that the probability of me escaping in some time for a given value of my total rate, some postulated value, is given by this nice Poisson relation. And we can then use this to say the likelihood of me seeing something new in some initial delta tau of MD for the postulated unknown rate, which is simply my postulated total rate minus what I've seen, is given by this. We can derive the likelihood. So this is sort of Bayesian, but we have the conditional probability from the Poisson distribution underneath. So then we can simply apply this a posteriori to all of our observed data. And so then we look at all the first escapes. We can say, and we can actually then put this into a big product form and say, what is the posterior distribution for my total rate, given everything that I've seen in each individual state. And what this produces is a distribution that goes to 0 when my unknown rate goes to 0. So this is basically total equals observed. Has a maximum and then decays at very large rates because it's extremely unlikely that I've missed a very, very high rate process if I've gone for many, many time periods at that rate. So we actually do use the width of this distribution to optimize the MD, but I'm not really going to talk about that today. But the main point is that we can take this data, we have this derived likelihood, we can use an information-free prior, use like the Jeffreys prior for this likelihood, and then we have an expected value of the unknown rate and the total observed rate for each state. So at every single cycle, we can just update this estimate, and we have an estimate for the total missing rate in our dynamics. So this is basically what we do. So in this Timbre code, we're sort of constantly cycling, and all the time, I'm accumulating this data for every single state in my system. I can then put myself into a big absorbing Markov chain, and for some initial condition, which really helps you drive what you want to look at, I can say, what's the expected time I stay in my known state space before I transition to this unknown state? And this is really a prediction timescale for my model. So if I say that I'm going to reach the unknown state in a millisecond, and I have some observable in my model that says a time constant of a second, I can't really trust that prediction, because in that second, there's thousands of things that could happen that I can't trust my model to capture. So this is really given some sort of UQ. Ideally, for any process we want to look at, we hope that our residence time is as long or longer than that in the time scale of the process we want to investigate. And we can also go, again, I'm not going to go into that in much detail, we can actually then it's kind of a funky derivative, but it's definitely possible to do. You can take the derivative of this unknown rate with additional computational work in each state. And you can use that to do a sensitivity analysis on this validity time. So then I can allocate the number of workers in each state is proportional to the gradient of this quantity with respect to additional computational work in that state. So it's like a computational optimal distribution of work to grow this prediction timescale as fast as possible. So that's the autonomous management of the tasks. We've also looked at sort of things like transition probabilities or committer type probabilities for these networks. You can think of other things, but this is like one figure of merit that we quite like. But we want to have, given the resources, it will carry on working until you say stop, and it's always trying to maximize the prediction timescale of the model. And that's again, sorry, just because to keep in fitting with we scale, we can go to, this is like nearly petascale, so it's not quite exa, but in principle, this works. So when you do this, you can go from these kind of simple toy systems, and you start employing sort of DFT level type resources. So this is it's a quick run of a few hundred cores for a couple of hours, looking at a die vacancy and some snap model of HEA. So here, I have the full chemical complexity. I can choose to collate my states via some local chemical complexity, and you can start to build up these type of graph structures, looking for things like sluggish or correlated diffusion mechanisms and things like this. So where you don't really see anything like this in these type of systems, which is quite general. We can go to look at stability of clusters. This is nice work from Kozmin's group with Sasha Goryeva, which just got accepted in HCOMs yesterday, I think. And so there this is looking at close-packed A15 Larves phases as precursors for dislocation loops in FCC metals. And we wanted to look at the stability of the different Frank loops and clusters in these systems. So we can run from here. We go a few thousand cores for a few hours, and we're really looking at the escape from this basin of this stable Frank loop structure. And then we can, in each one of these basins, really we can start to get an idea of because the way we're generating states is not just saddle searching, there's some kinetic relevance on how we're searching for the states. This is a sort of if you like, a meaningful sample of the energy landscape surrounding these type of defects. So we find many loops, we also find many more A15 type clusters, and it gives an idea of how we might start to characterize if you like, the microcanonical complexity of these type of systems. So that's for kind of more disordered systems. If we go to ordered systems, things become very simple. We can, the way we label these states is through connectivity graphs of atomic connectivity, and you can relate the graph isometries to space group operations. So you can very quickly take a periodic system and wrap it down to the translation, and then the space group as well. So you can break all this down to actually just sampling in 4 states. So therefore, you get all of the economies of scale, and all of my effective sampling times skyrocket in this case. So my unknown rates become very small. And then I can, as long as I work here, I can relate each transition with a jump vector. So for example, there's some cases like this case here. This is a self-to-self transition. So it's a little loop on this diagram here, but it does accumulate a displacement. So with these type of models, I can then generate trajectories, and I can generate spatial translation. And so then you can actually, you can treat this as a Walker with death problem. So I'm walking around, generating displacement, until I go to the unknown. And that isn't a typo, the 2 there. If you actually go work this through, you actually get this type of formal diffusivity. We can have an analytical expression using generating functions, which reduces to like Dallas-Trinkle's results when this unknown rate goes to 0. But now, because we have these unknown rates and we have detailed balance, we can very quickly do a Monte Carlo procedure to sample the allowed rates in my system. And then this can give bounds for my diffusion constants. This is like the 3 by 3 matrix of diffusivities. And then we can then put that in the diffusion equation. And it turns out the Kullback-Leber between 2 different diffusion equations is a time-independent spread. So we look at the solutions to the diffusion equation for given values of these bounds. And then we can then have a convergence metric, which is effectively the Kullback-Leber spread of all possible solutions consistent with detailed balance and my unknown rates. So this is a sort of toy example of this, where I have a one-dimensional system with 2 possible rates, and I can jump directly from blue to blue, or I can go to blue to orange to blue again. And I start out, and I have the indirect pathway, and this is some estimate. And as I go along, at some point, I discover this effectively is a toy simulation, but really we are doing the machinery that is the legitimate machinery underneath. So as I discover a rate, my estimate diffusion suddenly jumps, because now I've got 2 pathways. This looks non-monotonic, but if I look at the convergence metric, with the correct Lieber spread, this is actually a monotonically decreasing convergence for the diffusivity. So for a given set of initial conditions, the mean displacement from these initial conditions, my estimate is monotonically converging to this. So this is quite a nice property. We can apply this to look at, this is applying to this cluster diffusion problems. This is sort of quite anisotropic surface diffusion problems. And we have these Monte Carlo bounds that really kind of bound that diffusivity. And because we're only in 4 states and we apply this at scale, we can get to prediction time scales of a couple of months, so about 1 million seconds. So this is, we can kind of start to really think about being quite predictive with these things. You can also look at, this is a hexa interstitial in magnesium oxide, has quite a complex landscape. And it's quite deceptive. This single Arrhenius slope is just because the saddle point is almost exactly the same height as these barriers here. The actual, at higher temperatures, these very fast 1D diffusers do start to come in. And this is actually really saying that a simple diffusion constant is not necessarily adequate to describe these kind of multi-state systems. So we did some work to kind of take this up to a reaction diffusion equation, where we in principle have to work out this entire big spectrum, but we can use a sort of Bloch's theorem type idea and with spectral clustering to really kind of compress this and produce some nice reduced state models, which I guess just sort of saying that we did. Yeah?
I just have a general sort of thought. It's a little bit funny, I think, how you're presenting this, because you started talking about really wanting to model dynamics.
Yeah.
The examples you're giving are really cases where you're exploring the entire space. It really feels to me closer to where there's other methods. Like, I mean, I get that you want to revisit things.
Yeah, well,
you can make use, but a lot of dynamics things, they change over time.
Yeah.
You don't revisit states. Like, the examples you're giving are much more like.
So we require the diffusion problems. Yeah, we don't have revisiting, but the points that I had earlier on, like this example, we're not revisiting states. Here we're actually strongly. Our initial condition is looking at the landscape around this point. So we're trying to say, what's the stability of this evolving in time? If you have I completely agree that if I have something that's never repeating and continuously evolving in time, that's what I'm really going to talk about in the second part of the talk. So, but for sure, these type of methods, and this is one thing that motivates me to look beyond these type of methods, is that you require repeated visits to states.
Yeah,
so your scalability.
Contrary to wanting to do dynamics, where you often want to go from one place to someplace new.
Yeah.
For sampling, but there's lots of other ways to do sampling.
Yes, well, but you don't have the UQ if you don't do dynamics. That's kind of the fact that with our sampling is using dynamics is what gives us the UQ to manage things at scale. If we don't, because the real theoretical handle that's nice here is, and now this is, okay, this is not good use of time, but I am, where are we? This is the fact that this goes down with time. I do more work and my probability of escape goes up. And that isn't true for static methods. I don't have a proof of work for my sampling, right? I don't know if I run 10 dimer calls that I'm actually scaling 10 times. Whereas with dynamics, in this regime where I'm decorrelated, I do know that I have that. So that's why we're doing dynamics. We're running dynamics just simply for this reason. If there's a way of doing proof of work for other sampling schemes, happily use it. But that's the only thing. So this is we pay a lot in a sense, but then we're saying that CPU hours is going down in cost and human hours is going up in cost. So it's this is the other thing. Yeah.
I just want to comment. This is like the dynamics of a jump process.
Yes. Yeah. Exactly. This is exactly jump process.
Yeah. So this is not like flowing through a smooth landscape that is always going downward. There are pseudo equilibrium points.
There's yeah. It's thermally active hops. So it's what you call a jump process, right?
Is this to me?
Comment in general.
I think we all agree. Yes. Yeah. Thanks. Thank you. Yeah. No, it's definitely true. So, yes. So we use dynamics to discover these states and try to produce diffusion-type models. We can also look at something where it's evolving in time. This is an example of kind of these parallel methods. This is from Laurent Bellon's group, who I didn't mention on the first slide. So his student ran MD on 2 weeks on 10 CPUs to try and look at diffusion in disordered nickel-3 alumina. And we ran for 2 hours on 500 CPU and got a big landscape, which effectively we started here. This is exactly your point. So we started here, And there, rather than in the initial, for the UQ on the diffusivity, I was seeding with an initial state and saying, how far can I get from here? On each cycle, I'm taking the Boltzmann of everything that I've seen. So it will center the sampling on the lowest energy state it's found. So you do evolve in time. This is effectively a snapshot of the spreading out cloud of everything that I've seen. So this is actually, this is a problem where the long range order is changing with time. So we can capture that process. So the initial states were around here, and I end up around here, and I sample a lot of different complexities. And the nice thing about this is that it's unclear from this single snapshot of MD whether I'm representative of the environment. And we have lots of ideas on how to kind of interpolate between one single snapshot of MD and try to how we can best manage the allocation of tasks to kind of get an environment around a snapshot of MD. But but each time you do that, you sacrifice parallel scalability. So it's kind of there's always this kind of trade-off there. So when you do this, you can start to analyze the structure of the network, and you can put this into a mean field model to look precisely at the evolution with time, so the evolution, the aging, type kinetics with time. So we can what we were doing using this model for was that rather than trying to say we're producing this one kinetic trajectory, we're sampling and we're looking at the order-disorder transition on a local level, and we can put that into a mean field model, and we have some more sampling of this. So you can use these things to look at these more non-equilibrium problems. And also, I guess in the interest of, okay, yeah, I think I'll skip. So now we're going to this more continuous type of picture. How much time do I have left?
You have about 30 minutes.
Okay, oh, great.
Oh,
okay.
no, sorry. So we have lunch, but you have 25 minutes.
Okay, no, okay, we're good. We're doing okay. I'm not going to go back. I'll still carry on. We looked at, when you get these, okay, I lied. So when you get these very big networks, many states, the compound path probabilities can get extremely small when I have rare events. In fact, you can get so small that LAPACK overflows. You can't use, you have no eigenvalues, eigenvectors. You can't use spectral clustering of any sort. And there's various nice techniques that David's really looked at, but also Manuel Aten has really looked at, where you can remove states from your network whilst exactly preserving the mean first passage time between any pairs of nodes. And you can do that in such a way that you avoid overflow issues. So you can treat networks where their estimated condition number is 10 to the 60 or something like this, right? So extremely ill-conditioned networks. We put this into a Python code that you can do this quite nicely. Runs as fast as David's Fortran implementation. So, so then we also looked at, say, if I take some of these big systems and I start to remove nodes, rather than just try to look at the mean first passage time, can I really start to look at the first passage distribution? Which, when I'm looking at, say, the first passage from 5 to 3, those pathways might go through intermediate basins, so I can get these sort of multimodal type distributions. So at high temperatures, where the condition number goes down, I have access to the full solution. But at low temperatures, I don't. So we just sort of thought about how can we remove nodes from the network using this procedure to correctly produce these first path distributions. And what we find is that what you can do is that you can remove nodes quite a lot, but you have to retain the condition number in some sense. But there's actually, thankfully, there's lots of nice KMC routines that are well adapted for these two systems. They scale very poorly with number of states, but they can handle ill conditioning. So this is a way that we can remove the states into a form that's extremely efficient with these ill-conditioned KMC algorithms, and then we can generate these nice. So we effectively produce some sort of set of boundary nodes that connect communities, and this allows us to retain this dynamical fidelity, even though we massively reduce the number of states by many orders of magnitude. So that's just a somewhat. So now going away from this KMC type picture, going to talk about a bit more messy situations where we don't have quite as strong a theoretical handhold, but I'll try and argue what sort of progress we can make with these sort of ideas. So, as I said before, there's lots of systems where if you try to map it to KMC, you're going to come unstuck, right? You're going to have this is always something going on. There's lots of messiness. You can, if you close your eyes and think optimistically, you can try and say these are similar to fracture or something like this, but I'm not saying that. And there's lots of work trying to produce things like collective variables or reaction coordinates for these systems. And there's been some wonderful work to that end. There's some work using machine learning type ideas and these sort of ideas. But typically, these simulations are quite homogeneous in a sense. So if I look at, say, a nucleation problem or a single interface moving, these type of simulations themselves are quite restrictive in their phenomenology. And so therefore, I can try to think about producing a reaction coordinate. In these sort of cases where I have a big messy dislocations, or here I have twins, I have BCC structure, these big messy nanoparticles, it's pretty hard to even work out a priori what your reaction coordinate might be, and especially whether you could use that to meaningfully partition your configuration space in any way. So it's not really clear this is that possible. So what we want to try to do is to have a quite more agnostic form of coarse graining of the structures. We're going to use what we call these descriptor vectors. So we heard about this in the first few talks, which is great. So this is effectively, you can think of these as an incomplete basis set for many body environments. It's a wonderful illustration of this from Volker Deringer and I suppose Gabor and maybe even Christoph. So this is where we can typically think of functions, as we've heard about in a few different talks, some two-body functions, three-body functions, or higher order. I will be using mostly the ones implemented in LAMP, so the snap descriptors, or also we looked at things like angular Fourier series, and definitely we'll be looking at ACE and all these other ones as well. But we typically keep these to be, the things that are nice about the bispectrum ones is that they're typically quite low ranks. You can get a pretty good representation of about 50 or 60 functions. So this is quite nice for later considerations. So I'm really talking about coarse graining here, is saying that I apply some operation to my positions and I extract some observable. So I can think of that as a dislocation density for a certain type of Burgers vector, a crystal structure, a stress, which is not a scalar, but I'll come back to that, vibrational entropies, energies. This is currently just extensive properties, or scalar properties of the system. And in principle, they can be calculated. All of these quantities, if you look at them, apart from this one, but I will come back to this, look like you can calculate them as an average over local atomic environments. And as these functions are representations of local atomic environments, maybe we can produce an estimator for these observables just based on the descriptor representation of the structure. And what's nice is that we can go from, a lot of results I'll show will be going from 3n coordinates to about 50 coordinates. But I also will voxelize this data to have so you have 50 times the number of voxels, if you like. The estimators we're going to be using is just linear, so again, had nice introductions in the first two talks about this. So we're just going to we're going to say, well, how far can we get just using a linear model based on these descriptors to predict these quantities? So we've got really two parts to do here, which I have a graphic later on, but we're saying that first off, we can say, okay, I can coarse grain in descriptors, and I have my descriptor representation. I can then think about how to analyze this descriptor representation in terms of its geometry and also try to predict where it might go in this space. As a separate question, I can also take these descriptors and estimate properties of my system. So if you like, the descriptors are kind of my latent space for the dynamics. Linear models seem strange. Why would we use linear models? But if you think about a Fourier transform, this is a pretty good linear model. It can do lots of things, right? So if you go into sort of high dimension, you can do a lot with linear models. And also the other nice property that we have for a lot of these more spectral type descriptors, that they actually have a triangle inequality. They have a distance metric. So it's not just a kind of abstract form of similarity. You do have an actual metric space, which is quite nice if you try to think about trajectories or other sort of geometry inside this space. So we'll think about trying to predict these and treating these descriptor vectors as a sort of time series. So this is kind of, the spark of this kind of started when Cosmin and I had the great PhD student, Clovis Lapointe, who started looking at going, okay, we've done this for energies and forces. Can we go to vibrational entropies? This is nice because calculation of these things require the Hessian diagonalization. It's typically order n cubed to look at formation or migration entropies. Not always. There are some schemes. There are some order n schemes. So this is an example where we trained. So we effectively is very similar to DFT. I don't have a vibrational entropy per atom in the same way that DFT doesn't have an energy per atom, but I can still use my per atom descriptors to learn a total energy on a box. And this is an idea. So here I took, we also do have a theoretical justification of this in terms of the localized densities of states and things of this, but I won't go into that here. So our training data was looking at some small point defects in iron, and an MEAM model of iron, because it actually turns out if you use EAM with the splines, there's an intrinsic noise on this fitting. We're sensitive to the splining in the curvatures, actually. So if you do this, we trained on this, and then quite by accident made a bunch of boxes with loads of defects. The trained data is around 10 kb, and we can go up to about 250 kb of formation entropy, just in pure extrapolation, effectively. But again, you can think, well, this works when you think about that this is actually a sum of local environments. It's just typically when we think about these evaluation of these entropys, we do it in a phonon picture. We're immediately thinking about these long wavelengths and things like this. But if you can actually formulate it as a local approximation problem as well. And the natural next thing is to then look at saddle points and things like this. So this was, we can then train to look at the entropy difference, which is like a saddle point. And I think this is now run out of battery. But it's okay. And then we can also learn a similar model for the energies. So we have a vector for the entropy differences and a vector for the energies. And so then natural thing to look at there is things like compensation factors. So this is a sort of Mayer-Nadel compensation factor, and we can actually predict this factor just through a completely geometric interpretation of these parameter vectors. So this is like some things we can do with these linear models that go beyond just energies and forces. You can do quite a lot of different things with this. So now we want to try and go beyond that. So we've looked at vibrational entropies, but can we use this to really target more general microstructural properties? And in general, you expect this to work because all the properties I'm listing here, you can think of as a sum over local environments. So if I have a representation of local environments, these type of descriptions should work pretty well. Yeah, that's basically what I said. There is an issue with scalar and tensor, which I will get to, and there's lots more work to be done. But most of the time, I'm going to be working with proper scalar-valued descriptor points. So this is the idea. So we can see why this might work. This is an example of saying I'm just taking my descriptor vectors summed over voxels, and I'm whitening it and looking at the deviation from the mean. And this is what all the coloring each voxel is. And you can see that I'm already sensitive to my defect content just from the deviation from the average values of my descriptors. This is already encouraging, saying that I should actually be able to be sensitive to the microstructural properties in this system. So more generally, we can do that. So this is now a model that I'm training on large boxes, and I have a total dislocation length from a veto, and I'm treating that as my training data. And then I'm then applying that model to look at the signal from individual voxels. And you can see that I'm picking out all the microstructural properties here. And this is for the total dislocation content, but I could think about changing up that theta vector to anything else and try to look at other properties. And so what's nice here is that I'm training, just like in DFT, I'm training on my total signal, but then I can actually apply it at a local level, and I have this local sensitivity. So this is, and of course we could train on the local quantities as well. But this is quite nice. So this is sort of an example of the type of things we can get out from this. So this is sort of screw dislocation content or all total dislocation content, a certain type of Burgers vector, the pressure, HCP content, and number of dislocation junctions in my system. And because these are sums over local environments, I can massively truncate or sparsify my training data, and my predictions kind of stay the same. Yeah, I think it's not working. So more generally, this is like sort of looking at a larger catalog of mechanisms. There's kind of lots of plots here. But it's more, we've got some nice diagonals, and then there's a few ones where it doesn't work at all, right? And, okay, I can maybe point in real time. But the suspense. I think I managed to, okay, so these ones don't work well. So you'll notice that all the times where it doesn't work very well, and in fact sometimes where it does, it's because I'm looking at a quantity that's actually a matrix. So the stress is a 3x3 matrix. And here I'm looking at the covariance of the Burgers vector, so that's also a 3x3 matrix. And whilst I'm contracting them in principle against these Cartesian vectors, this is really a matrix property, and it has no right to work that well as it does here. And in general, oh, did I already change? Okay, there we are. So yeah, you can see it works a bit, doesn't work very well, it doesn't work at all here. It's completely insensitive to these properties. And these are all because of the tensorial nature of the actual thing I'm trying to regress. So this is because these descriptor vectors are scalars, which I use PCA to reduce it a bit and whiten, which is more important for the next part. So I can capture these properties if I go to a 3x3 value descriptor. So this is just the virial of my descriptors, which is actually implemented in LAMMPS already. It's how you extract stress in a snap potential. But this was an EAM potential underneath, actually. But it still can capture the stresses excellently. And to within some form of discretization or a few errors in the veto, well, not errors, just as discretization points, it's a bit subtle to see exactly where the error is coming from in these cases. But I can actually capture quite a lot of these properties. And going to a fully equivariant model is kind of in the works, effectively, to look at these properties. But when you start to look at the actual distribution of these vectors, the other nice thing you see is that they're pretty unimodal. So this is for 60 different copies of this big uniaxial system. And I'm looking at the total descriptive vector signal and the histogramming that. And you've seen that it's fitting this nicely unimodal distribution. So in this case, we can start to think about outliers and extrapolation grades from active learning. And what's quite nice here is that there's various measures, approximations to look at this. We're just going to use a simple one that assumes I have this property where my underlying distribution is a Gaussian. And this is called the Malherbe distance. So it's a form of extrapolation grade. So this is quite nice because this is whatever modeling we might try and do, this gives us a measure of how far I am from my training data and is a form of uncertainty qualification, effectively. So it's similar, it's what you get, as James was saying, so it's kind of mixed up with how you would get uncertainty from Gaussian process type ideas. They mix up the epistemic uncertainties and this sort of extrapolation uncertainty just from distance from my training data. We try to really isolate these type of measures. When we start to build models on top of data, we will get epistemic uncertainties, but we won't have any measure of extrapolation. So the standard sort of UQ ideas of propagating uncertainties we will have, but then this is used as a backup, as an essential backup to have a measure of extrapolation in addition to the interpolation uncertainty. So just a few notes on this sort of process. So the general idea is that I could run some MD, at some sparse snapshots I can dump the positions, and on a much finer timescale I can record all my descriptor vectors. And this is highly scalable. This, for the exascale flavor of this conference, this is very scalable possible. There's very little storage involved. And I can actually interpolate the trajectories. So this is an example of where I'm dumping things on a coarse timescale, and that's the red dots here. I'm applying DXA to get the dislocation density. And then I can have my descriptors interpolating these points. I can use my descriptor model, and I can then predict the dislocation density on a much, much finer timescale. So something that would be very complex. Just the logistics of doing this at scale, when dumping things every few picoseconds and applying the code and everything like that, is this is hard work a lot of the time, and there's a few technical difficulties there. The other nice thing about this is that, in principle, we don't actually need to select any coarse graining objectives a priori. So this latent space is sufficiently rich that we can capture many, many properties, so I can decide after the fact what I think is important. Or I actually don't necessarily need to work in observable space at all. I can just use this latent space and start to think about trajectories in that space. And one thing about doing that is because if we choose these well, we have a metric space for our descriptors. This is quite nice when we start to think about trying to look at diversity or other analysis of trajectories in this more general space. So a few little examples. There's lots more that can be done here, but a few examples of this. This is for this uniaxial tension example. This is not greatly shown. This is actually an ensemble of 60 different simulations, and I'm looking at the median and 40, 60, and 20, 80 percentile ranges. So basically, we're saying that this looks like a muddy orange because the black and the orange are on top of each other. This is an estimation using descriptors extracted from the MD. So I'm not generating anything here. I'm just applying my models on the descriptor basis. But I can then say, okay, once the flow stress has a negative slope, I'm saying that I'm yielded. I can take 20% of my simulations, train a model, a classification model based on that yielding, and then apply this to the other 80%. So I can sort of classify yielding or classify microstructural changes just based on the descriptor vector. You can also then start thinking about the ensemble average of this descriptor vector trajectory. If I apply PCA to this, you can see the yielding is actually, I have a dividing surface in this space for yielding. So I have effectively a yield surface in this space. And post-yield, I start to become much more localized, and I can just characterize from where I am in the descriptor space the properties of my system, whether I've yielded or not, or other plastic properties. So there's a lot more things that you could think about for analysis here, but this is quite a nice metric, small dimensional metric space where I can start to use all these tools from machine learning to look at trajectories. So final thing I'll talk about is trying to use this to go. So we've done all this part effectively. So I've sort of dumped things, interpolated them, and start to analyze the dynamics in this space. But can I really look at future behavior and try to predict things forward in time? There's lots of different tools, neural network ideas to look at time series and things like this. I'm just going to use one of the simplest tools that are around for a long time ago. So it's called the vector autoregressive model, a p-state vector autoregressive model. It's very simple. It's saying I'm estimating the next step of my trajectory by a weighted average of the past p steps, and then I have some Gaussian noise, some weighted, so some aleatoric noise here. And I was trying to make a few qualifiers on this. So it's Markovian in the stacked history. So it's Markovian in the last p steps, this model. And it's also unimodal in those last p steps. It converges to a unimodal distribution in those last p steps. But that's quite a lot you can do with that. It's linear, but in high dimension with these type of things, there's quite a lot of structure you can have in a linear model in high dimension, as we've seen. It's similar to a sort of a dynamic mode composition or Koopman type approach, where you have sort of a linear expression of my Koopman operator. You can argue this, but this is, you can make some argument it becomes like this. And because of this function form, it's quite flexible, but we're really applying this to large or disordered simulations where there's always something happening, there's always evolution, continuously evolving, and we're saying that we're remaining unimodal in this descriptor distribution. So there's no unseen macroscopic changes of my system. So that restricts the type of application regime, but it does still, I think it still allows for some, when it comes to, there's the forecasting, but also actually resampling these trajectories and increasing effective ensemble sizes, it can really do this quite well as well. So I'll give some examples of this. So a few more qualifiers. So one really nice thing is actually very similar to what James was bringing up before. So with this type of model, you can show that the max likelihood solution is just the answer you get from L2 regression. So I can do some maximize, or I can minimize the cost. We typically do this with a regularization. And then the noise, which is definitely not diagonal, comes out, it's extremely non-diagonal actually, comes out through the covariance of the deviation from these properties. So that's the max likelihood solution. The full, as James mentioned in the talk, so to actually try and do the proper epistemic propagation to these parameters gets hard in high dimension. And there are various techniques. Our solution was very similar to the committee type approach that James was talking about. So I use what's called bagging. So it's effectively a non-replacement bootstrap where I take random samples of the data and form many models, fit them all, and then look at the distribution of the parameters from these fits. And they're usually fairly tight. And it's very robust to the exact ensemble sizes you pick. So did try a few other ones, but with more nonlinear models, it gets very sensitive to overfitting, and the treatment of noise becomes, to actually unambiguously define what you mean by the aleatoric noise, it becomes difficult. By aleatoric, I mean, this isn't a measurement error, this is a fundamental fluctuation of the system. It's like a thermal vibration, or in a more general sense, like a Morris-Vancic sense, this is the information loss from coarse graining, produces a stochasticity. So I'm rejecting degrees of freedom, and then this is expressed through a stochastic expression, stochastic force on here. So what can we kind of do with this? This is a simple example of these nanoparticles. Start from something fairly disordered, and you run in time, and it goes to something more FCC type structure. So I train on the first half a nanosecond, and you can't really see. So what I have here is orange is my prediction. This is an ensemble of 60 simulations. And the blue is the epistemic errors, which you can't really see here because it's already shooting off to craziness very quickly. So here the epistemic errors also look quite small because they actually have quite a lot of data. And in this regime, the fitting from the Bayesian fitting would say that we have quite low uncertainty. But if you complement this with an extrapolation grade, you quickly see that I'm moving way outside the regime in data space where I actually train my model. So I shouldn't really trust these. I shouldn't trust these results. I'm already at 4 sigma after a few nanoseconds. So I can't really trust even though my epistemic interpolation uncertainty is low, my extrapolation grade says that I'm really bad. So I can't trust this model. If I then add a bit more now, 1 nanosecond to total training, we're starting to look at something a bit more reasonable. The epistemic errors start to come in here as well. And then generally, this means, as you might expect, the epistemic has a larger distance away from my training data over all the models. But I'm getting much closer, and I'm getting to within 2 sigma, and I'm sort of looking like I'm getting pretty close here. And then if I add some more, I really I'm down to into 1 root 2 sigma type regime, and my models are starting to look a lot more realistic on the actual system. This is quite a simple, this is a case where I am actually evolving in time, and there's no steady state necessarily, or I'm getting to a steady state. And you can do a Chapman-Kolmogorov on this for people who do these sort of things. So this is we have a Chapman-Kolmogorov in the time interval times the number of history, and we can show we have convergence in this for these types of systems. So you can try some more complicated things. This is a cyclic shear in copper. So I actually have 2 models. This is an earlier work where I have 2 models, one for positive and one for negative shear. So in effect, this is very, very poor use of the training data. So effectively, you can imagine it's half the training data per model. But I apply it, and I can actually then, with those models, I can change the cycle period as well. But you see, so at first, I get something that looks stable in the mean, but the epistemic uncertainties start to go up. And also you can see that the epistemic uncertainties of the predicted model are spiking at the yield points here, which is what you might expect because it's this point of transition, there's a lot happening, and I've only seen it very rarely in my cycles. So I see that my uncertainty qualification is really saying in these type of yield points, I'm quite uncertain. But if I add some more data, I can go down, my epistemic errors remain low, and I have this quite stable prediction of the cyclic evolution. You can look, and then you can track, for example, the decay of the dislocation densities, character dependent over the time of the cycle. I also want to make a point quite clear that all these orange lines that I'm generating with this model start from the same initial conditions as MD. I'm not starting them here, I'm starting them at time equals 0. So I'm resampling all of the MD trajectories with my model. So even though it's a linear model, it's capturing all of this yield surface and all of these properties here. So this is saying that when I'm in high dimension and linear, I can still do, I don't just get exponential decays, I get, when I start to project high dimensional dynamics onto these low dimensional observable spaces, I actually can get quite complicated things. So this is a question of this, this is another example of this uniaxial tension example. So again, I'm training over this region, but I'm starting my simulation at the initial time. So I'm capturing the spike and the drop in the flow stress. Again, it's a bit cheeky because this is actually not strictly speaking, but it's kind of a scalar, but I can discuss this more. But then because I'm just predicting the descriptor evolution, I then apply my observable models, and so I see this peak in the flow stress, the drop in Hertz dislocations as we expect for this type of system, the rise in the pressure, the amorphous content also increases because there's quite a high strain rate here, and you can see that initially there's very few 1/2/6 dislocations because I'm forming from an initial seed of loops. But then these grow and then stabilize as I start to increase in size. So you can see that on this movie here. So initially, it's quite a small snapshot, but I start from loops. So I have Hertz dislocations and very few of these partials. And then when I start to increase, the dislocations come up and the Hertz loops disappear. So, and what's nice is we're resampling the yield point. So what this means is actually quite nice, is that I can take my initial conditions from MD, I can fit this to some unimodal distribution, and then it's quite easy to resample, produce 100 times more initial conditions, and then propagate these. So the black dots is a noisy MD histogram of my 60 MD samples, but it's quite easy to generate 6,000 of my initial conditions that are within the same distribution. And then I can that's my initial conditions, and then I can propagate those through time, and I can then turn these quite sparse histograms into nice smooth distributions in time. And this is a few minutes of computational effort for the entire start to finish procedure. So that it's quite stable and it's very cheap to fit. So you can do quite a lot of things with this. So I think that's oh, and yeah, we also looked at some cyclic things. So it's a different different approach where I'm just taking one snapshot every cycle. I can train on the first 4 cycles a big ensemble of these tungsten rhenium boxes. You then test it on the next 4 cycles, and then I stop because this is quite expensive. This is a logarithmic timescale, like it's a steady state, and it's kind of fit to some sort of Cox-Mecking recovery laws or these sort of things. So you can kind of get to some mesoscale ideas here, and definitely that's the sort of future direction of all this. So I think with that I will finish. I will just do one last advert, because I didn't talk at all about force field uncertainty, and I want to stress that I've got a postdoc about this. So saying, to advertise the postdoc, our lab is in Marseille in the south of France. So it's just south of the nice city of Marseille. But more importantly for the lab itself, it's also very close to these nice national parks nearby. So if you want to come and do a postdoc looking at some of these energy landscapes, but trying to look at, this is but no, if you know anybody's interested, let me know. Yeah. Okay, thank you.
Okay.